So our first lecture will be given by Professor Rebecca Flint from Iowa State University, and her title is Multi-Channel Kondo Physics from Intrinsic Criticality to Unconventional Orders. Please take over.
All right, thanks very much. So yeah, I'm going to talk about multi-channel Kondo physics, and I really want to encourage people to ask me questions at any point. So please stop and ask me questions at any point. So how if I turn that on? Okay. Okay, hold on a second. Take this up. All right. So that was my pointer. Yeah. So I'll just use the slide advancer. Okay. So no, it's not a pointer issue.
The pointer has like
no, it's fine now. Actually, it was just not then. All right. So this is so this is what I'm going to talk about. So first, I'm going to review some single-channel Kondo physics, which I'm sure Chimao has talked about to a certain extent, but I'll review it from what I think will be a useful perspective to understand how we go beyond single-channel Kondo physics, where you can either get under or over screening of your Kondo impurity. We'll talk about how you can realize this in real materials, what the physics you get out of multi-channel Kondo impurities is, where you see that they're intrinsically quantum critical and host exotic excitations. And then I'll talk about what we get when we take this to the lattice. And there's not really any good examples of multi-channel Kondo lattices that are likely to be realized in real life. So we'll focus on the two-channel Kondo lattice, different phases, and what we know about the phase diagram. So for single-channel Kondo physics, let's start at the very beginning. So the basic idea is a magnetic impurity in a metal. So we have iron and gold as sort of a classic example. We have conduction electrons, and then we have an antiferromagnetic interaction between the conduction electron spins at the origin and a local moment at the origin. And so this gives rise to spin flip scattering, which is a new kind of scattering that allows this local moment to start to sort of scatter off of these, or have these conduction electrons scattering off of the local moment. The spin flip scattering leads to a logarithmic rise in your resistivity, which gives you a Kondo minimum at temperatures where you sort of have you're losing your phonon scattering as the temperature decreases, but increasing your spin flip scattering. And at high temperatures, you see the free local moment in your magnetic susceptibility. And as you cool down, you get more and more spin flip scattering. So this is a static sort of picture, but you should imagine this is really a dynamic picture. And overall, these are forming a Kondo singlet. And at low temperatures, you quench your local moment, so you have a constant magnetic susceptibility. Sometimes it looks like this, sometimes it's flatter. And we say that this screening has onset at the Kondo temperature, which is given over here in terms of the conduction electron bandwidth and the Kondo coupling. And down at these temperatures, the Kondo coupling, the Kondo temperature is the only scale in the problem. So your Kondo coupling has flowed to infinity. It has a strong coupling fixed point. And down at these temperatures, you see Fermi liquid signatures coming from the contribution of the impurity. So you have a linear specific heat, you have a constant impurity entropy, and your resistivity can have this T squared term, and all of these are enhanced. So gamma and chi naught go like 1 over Tk, and A goes like 1 over Tk squared. These all behave essentially like 1 over Tk behaves like an effective mass that can get very, very large. So this is the basic idea. What we also say is that the local moment is asymptotically free, so you can make a connection to the physics of quantum chromodynamics. At high temperatures, your local moments and your quarks are free. At low temperatures, they've been bound together into mesons or Kondo singlets in this case. All right, so that was the impurity. And now we can talk about what happens when we go to the lattice. So here we have a lattice of local moments, and at high temperatures, again, they're decoupled. So here we just have this coupling, antiferromagnetic coupling at every site on the lattice. And we know that at low temperatures, one possibility is that you again screen your local moments, and what you end up with are heavy fermions. And these can be 100 to 1,000 times more massive than the bare conduction electrons. So the easiest way to understand this is to look at it in momentum space. So if I take this Kondo Hamiltonian, what I want to do is replace this spin by something that I can do quantum field theory with. So I represent it in terms of pseudo fermions Fs, where I have a constraint also that my Fs are half filled. And then that perfectly represents this spin 1/2 spin. Here, there's a spin index on here that's been suppressed. But since these local F electrons have no dispersion, they just give you a flat band. So they're shown in blue here, whereas your conduction electrons are dispersive and they're shown in green here. And so we talk about these as F electrons as sort of the common language, but at this point, they're not electrons. They don't actually have any charge. They're just spin-ons, but they acquire charge from conduction electrons. And practically speaking, the F electron ends up being a type of composite fermion, where the way you add an F electron to your system is to take, if you, in terms of the sort of original components, which are conduction electrons and spins, is that you can add your conduction electron and flip a spin at the same time. And so this combined gives you a composite fermion. All right, so these are our ingredients. This is what it looks like sort of at high temperature. And we can solve this in mean field theory, where I've taken this S, put it in here, introduced a mean field that acts like a hybridization. So this is our Kondo singlet. It's the expectation value of C dagger F, where I'm summing over sigmas, so it's a singlet. And the overall Hamiltonian now looks like this, where I have dispersing conduction electrons, sort of dynamical hybridization between my C's and my F's. I also have a constraint term that enforces what is usually half filling, but I'm keeping it here as an arbitrary filling Q. So for SU, this is justified in the SUN limit. So for n equals 2, this is a filling of 1, which is the sort of typical example of when you have a spin singlet, or spin a ground state doublet that is singly occupied. Okay, so now once we turn this on, we can take this V and say it's uniform everywhere. And my lambda is also uniform everywhere, so I'm only enforcing the constraint on average. And in this case, I get a hybridization between my C's and my F's. And so this is the hybridized band structure. So a couple of things have happened here. So one, the conduction F electrons have hybridized. This happens sort of gradually as a function of temperature. It doesn't break any symmetry, so it happens as a crossover. The F level has renormalized itself. So if we go back, this was sort of down deep in the conduction band. This is really like the lower Hubbard band of the spins. But it now renormalizes up to within TK of the Fermi energy. And the Fermi surface volume has enlarged. So again, let's go back. Here's the Fermi surface volume here. This, I didn't label it. It should be EF. And then here, it's sort of out here. And what it's done is it's incorporated the F electrons into the heavy Fermi surface. So another thing we see is that you get a much flatter band. Note that the excitations that you have are now these linear combinations of C's and F's. And the blue and the green represent sort of the relative contributions of the F's and the C's respectively. And so you see that out here, near the Fermi energy, it's mostly F-like and it's pretty flat, which means it's a much heavier effective mass. You also see that you develop a hybridization gap. This happens either above or below the Fermi energy typically, unless you happen to be tuned to the correct filling where you get a Kondo insulator, in which case your chemical potential sits inside the hybridization gap. And this hybridization gap, here this V is this sort of mean field parameter we had here that's like this expectation of C dagger F. This grows roughly like the square root of TKD and gives you the direct gap, and the indirect gap is around the order of TK. All right, and all of this onsets at a crossover temperature scale that's called the coherence temperature, which is T star. So when your resistivity comes down, you have an increase, which is your spin flow scattering, and then you start to develop coherence, and you get a heavy Fermi liquid. And you get this sort of Fermi liquid behavior where your resistivity goes like T squared, your specific heat is linear in temperature, and your susceptibility is constant. And all of these look like they're basically a normal Fermi liquid, except with a very enhanced effective mass. So I want you to keep this in mind as we go and make life more interesting and add different variations on this sort of simple single channel Kondo effect, because we'll get different kinds of scaling behaviors. All right, as I said, if anyone has any questions at any point, please just interrupt me. Ah, good. Okay, we'll go with you first.
Yeah, I do have one question. So, can you maybe explain a little bit about this large n limit? Because I'm just not familiar with that.
Sure, yeah. So let's go back here.
It seems this is required to justify your mean field.
Yeah, so you can always make a mean field. You just don't always have a controlled mean field. So you can, with large n, you can do expand in your fluctuations. So here we take this and for SU2, we have these spin indices sigma. So sigma is normally like plus or minus or 1 or 2 for SU2. You can generalize this to a model of SUN spins, and this is actually very well justified for a lot of F electron materials. And so then your sigma will range from, say, 1 to n. And in that case, you're summing over these sigmas here, so this becomes exact mean field in the large n limit. So as long as, so in that case, this sort of statement here is exact where these VJs and these lambda Js are your mean field parameters. So does that answer the question?
So large n just means I have many local moments?
No, it means your local moments are not, so here you have a local moment at every site, but your local moments are not SU2 moments, but they're SUN moments. So instead of having a doublet, you have n states. So one way you can get slightly larger n is to go to the rare earths where you have J instead of S. And so then you can get like SU6 for cerium, for example, or SU8 for terbium. All right, you had another question? D is the bandwidth, yeah, of the conduction electrons. Yes. Yes, that's, yeah, so that is a different, like it's a different mean field theory. Normally you wouldn't want to use fermions to represent your spins. If you do that, you typically will use bosons and do Holstein-Permikov bosons in sulfur magnetic order, which is absolutely another possibility here, as we'll talk about. It gives different physics, yeah. Yeah, so generally when we're talking about heavy fermion physics, we're looking at like the fundamental representation, which is like the spin 1/2 representation. And that tends to be what's relevant. But you can certainly also have larger spin representations when you have something like iron or manganese as your impurity. All right, any other questions? Okay, so, all right, so, just want to say sort of briefly about the phase diagram of this Kondo lattice model. This is a very complicated question. Rather, it's a very rich phase diagram, but this is the very basic idea, is that you can have this heavy Fermi liquid that I just told you about, or you can have, as we were just discussing, magnetic order of your local moments. So they interact via the RKKY interaction, which I'm not going into details, but it basically is a Kondo coupling between your local moment at one site that then propagates through the conduction electrons to then couple to another local moment. And that can be either ferromagnetic or antiferromagnetic, depending on the details in your system. So it's often antiferromagnetic, and here I switched from D to rho, which is 1 over d, the conduction electron density of states. So we have a competition between this formation of a heavy Fermi liquid at this T star or Tk, which is exponential in -1 over the Kondo coupling. So it's very small for small Kondo couplings and then increases very rapidly. And then we have this RKKY coupling that favors often antiferromagnetism, and this goes like the density states times this Kondo coupling squared. So you can just sort of sketch these two dashed lines for those two scales, and they cross at some point. And so we expect a heavy Fermi liquid below T star, and we expect some kind of magnetism below the antiferromagnetic ordering temperature, and naively, there should be a quantum critical point here. And this is a huge question that I'm not going to get into in great detail, but I just want to give you the flavor. This is called the Doniak phase diagram. Often in real materials, this quantum critical point is screened by superconductivity. And when you add in the fact that you can have different lattices with magnetic frustration, you can have much more complicated phase diagrams where you have competition between not just your heavy Fermi liquid physics and magnetism, but also heavy Fermi liquid physics and spin liquids or other types of frustrated magnetic orders that don't break spin rotation symmetry. And so as Qimiao has done a lot of work on, you can also have basically changing the size of your Fermi surface, whether or not you're incorporating the local moments into the Fermi surface. This can happen either out between your heavy Fermi liquid and a spin liquid, or it can happen inside the magnetic dome where you have a large Fermi surface magnetic order that transitions to a small Fermi surface magnetic order. Yeah. Yeah. Okay. I mean, so you usually expect superconductivity to rise from fluctuations of your magnetic order is typically where it comes from. There's other possibilities, one of which I'll talk about later in the lectures, probably tomorrow actually, which is composite pair superconductivity that can arise from two-channel Kondo physics. And I think it's still kind of an open question of why we get superconductivity in some cases and not in other cases. Yeah, so I'd say most of the time you can get superconductivity, but there's many cases where you don't also. So heavy Fermi physics is complicated. Yes, question.
Yeah, the Kondo coupling member, is that material dependent? And is it like something that you can calculate, or is it something that I have to guess or less?
Okay, so I'll show you where it comes from like from the higher energy models shortly. So you can calculate it in a model perspective, whether or not, how you know exactly what your Kondo coupling is for a particular material is not so straightforward, I think. Yeah.
I have a question regarding the pairing mechanism for the superconducting cell.
Sure.
You said the magnetic fluctuation may matter here. However, the superconducting region covers under the AFM region as well as the other side of the critical point. And do you think the magnetic fluctuations are the same on both sides?
I mean, I guess I'm imagining that it's, fluctuations like paramagnons in the high temperature phase are what's typically, I mean, there's nothing particularly concrete. You can also model the superconductivity without involving an exchange boson, but the sort of simplest picture is to use magnetic fluctuations above the ordering phase, but you do, in real materials, actually get like this line extends through here. So you get superconductivity both in the antiferromagnetic order and outside of it.
So around the quantum critical point, the large fluctuation.
There's a lot of fluctuations around the quantum critical point. That's sort of the basic idea. It's not clear that that's always the only thing that's going on, right? This is a very overly simplified picture. Okay, other questions? Otherwise, I think we're gonna, okay, I wanna say just one last thing to sort of, okay, so I'm not gonna give, this is a very incomplete overview of what we know of the Kondo lattice from numerics and Fokker is going to talk about the quantum Monte Carlo stuff later. I just want to bring up one thing that's going to be useful for me comparing to the two-channel Kondo physics later, which is that you can solve the one-dimensional Kondo lattice model numerically exactly using density matrix renormalization group. And there you don't find a heavy Fermi liquid because it's one dimension, but you find a heavy Lettinger liquid. You also find ferromagnetism. And here I'm varying the conduction electron filling, NC. And this is the Kondo coupling divided by the kinetic energy. And if you go all the way up to half filling of your conduction electrons, which is 1 here, then you actually get a Kondo insulator phase because your chemical potential is in the hybridization gap there. So one thing I want to see, and this is, I should note, from a different paper, which is a slightly different model, but effectively they're going along this line through the heavy Lettinger liquid. Here, this is the Kondo Heisen. Anyway, what I want to show you is this is a Kondo lattice model. So this had spins and conduction electrons only. And what you can calculate is the conduction electron momentum distribution. So this should look like a Fermi step function as you go through K. And here is the Kondo coupling is 0, and it's just stepping through at a light Fermi wave vector here. And it looks basically like a typical discontinuity. It's not fully discontinuous because it's actually a Lettinger liquid. But that's sort of the basic idea. But as you crank up the Kondo coupling, you no longer have a transition here, but you have a discontinuity at this larger Fermi wave vector here. And what this shows you is that you've actually incorporated the spins into the Fermi surface. And this is, I think, really cool because there actually weren't any F electrons here ever. There were only spins, but they get incorporated into this Fermi surface. So we'll see similar things when you get two-channel Kondo lattice, and I'll explain in more detail there because that will be my actual data. Yes?
Is the Lettinger theorem here, well, as the Fermi surface drastically changes?
Yeah, so it satisfies Lettinger theorem for just like C's for this guy, and then it satisfies Lettinger's theorem where you've included the spins into the Fermi surface. So you enlarge it by essentially 1 fermion per site.
Oh, okay.
Yeah.
So it's just basically including extra 1/2. Is that true?
Possibly.
Okay.
Yeah, I'm not 100% sure, and this is mildly more complicated because there's a Heisenberg coupling here as well. But I think that's probably correct. Okay. So this is sort of typical things. And now here's the stuff I'm not going to tell you very much about. So people do dynamical mean field theory. You can do a lot of other types of numerics. And what you generically find is generally consistent with the global Doniak phase diagram. And there's still a lot of big open questions about what's happening at that quantum critical point. And I don't really want to get into that because that's not the topic of this talk. But so, yeah.
Yeah, so I have a question. How do we interpret the data like over 2 and 3, like the green and blue line? It seems that there is no.
Yeah. So this is probably, I mean, you got numerical resolution issues, so it's unclear that you're seeing, there could be a jump that you're just not seeing there. It's not super clear to me. Yeah. So this is from this paper, if you want to look into it in more detail. All right, so now I want to talk about sort of variations from the simple single channel Kondo model. So I'm going to start with the simplest possible thing, which is to add a spin degeneracy to our local moments that can be larger than spin 1/2. So we're still thinking now SU2 spins, but I'm letting them have, say, spin 5/2 or spin 3/2 is what I'm actually drawing on here, instead of spin 1/2. And I'm also going to add M conduction electron channels. So these are just different numbers that I'm putting extra indices that I'm adding here. So M ranges from, little m ranges from 1 to big M. And I can have, in principle, different bands, and these can couple. So this is diagonal in M, and I have a JK that can be different for different M's in principle. What we're interested in is when these JKs where these different channels are related by symmetry. So one way you can think of them is that, like, say, your conduction electrons come from d orbitals, and you have 3 degenerate T2G orbitals, and those are your conduction electrons. And so those would all screen the same local moment with the same Kondo coupling. And that would give you basically 3 types of spin 1/2 conduction electrons in this case. So the physics that you can get from this is dependent on how this M and this S are related. So perfect screening is when the number of channels is equal to 2 times S. So if I think of a spin 3/2 local moment, I can imagine constructing it out of sort of 3 spin 1/2 moments. That's what these arrows are meant to represent. And then when I screen it, I have 3 spin 1/2 conduction electrons, which are now really different arrows in different channels that are represented by the 3 different colors here. And this forms a Kondo singlet, right? It's perfectly screened, so this is still normal, the same physics as in the single channel Kondo lattice. We just call it perfect screening instead of single channel, but it's the same basic idea. Life gets more interesting when they're not matched. So if we don't have enough types of conduction electrons, you can get partial Kondo screening. This is called under screening. And so you get a remnant spin that is just take this, subtract this. But what's more interesting is when you get over screening. So this is what gives you multi-channel Kondo physics. And this is intrinsically quantum critical, meaning when these JKMs are all the same, so we have this degeneracy, then we get very interesting physics. And so I'm going to give you just a little flavor of it here, and we'll come back to it. So if I have my spin 3/2 local moment, here I'm assuming I have 4 different channels of conduction electrons that can screen it. So they all try to, right? Because they don't know how to choose which one. It's an impurity, they can't break a symmetry. So they all try to screen it. And so if I look at this and I add it up, I started with spin 3/2. After I try to screen it, I have spin minus 1/2. And then I try to screen that spin minus 1/2. But I do too good of a job, and so I get back to having plus 3/2 here. And then I try to screen that, and I get minus 1/2. And then I try to screen that, and I get plus 3/2. And this process continues on forever, right? It tries to screen it. This is saying it's just never succeeding. It's not going to make a Kondo singlet out of this case. So this is what leads to the weirdness in multi-channel Kondo physics. So before we get into more details of it, I want to talk more about where it really comes from, because I don't know any real good examples of where you have this kind of multi-channel Kondo physics coming from SU2 spins with larger spin and different channels. But there are various ways of getting it. So to talk about where we get 2-channel or multi-channel Kondo physics from in real life, I want to talk about where we get Kondo physics from. So this is going to answer one of your questions from earlier. So if we go to the higher energy scale model, we get Kondo physics from an Anderson model. So this is a simple Anderson model for an F electron that can only be at most doubly occupied, which is not true for real F electrons, and we'll get there. So I have non-interacting conduction electrons. I have an on-site hybridization between my local moments, or my Fs and my Cs. These are now real Fs. I have a chemical potential for my F electrons, and they have a hover du. And so we'll often draw these atomic level diagrams where I am just looking at the impurity, or the F. This is a lattice, I guess. So I'm looking at the impurity atomic state. So I can have either one F electron, in which case I have a doubly degenerate state, and that's going to be my ground state. I can have 0 F electrons, and that's a singlet. And that costs me this modulus of epsilon F. And then I can have a doubly occupied state, which has an energy U minus 2 epsilon F. So all that just comes from, these energy scales just come from here. And this is the basic model from which you eventually get Kondo physics. So I'm not going to go through how you get there. It's a Schrieffer-Wolff canonical transformation where you're essentially integrating out the high energy degrees of freedom. And so you no longer have these as real states in your system. So you only have a valence of 1. And these are virtual valence fluctuations here, from here to here or here to here, that give you a antiferromagnetic interaction between your local moments and your conduction electron spins at the same set. And in this simple picture, this Kondo coupling, JK goes like this V squared that is up here and is mediating these valence fluctuations over S1F, and you get the same contribution from both of these two things because both of these excited states are singlets. Good. Okay. So this is how we get the usual one-channel SU2 Kondo model. Now, in real life, we're often looking at Kondo physics in rare earths and actinide materials. So these have 4f or 5f electrons. They have a very strong spin-orbit coupling. And so we generically get SUN physics, where n is 2j plus 1. So let's look at cerium. So cerium 3 plus, you have 1f electron. That gives you j equals 5/2. There's also an excited j equals 7/2 multiplet. That's a pretty high energy scale, so we're throwing it away. And so now I have 6 states here, so this is SU6. And so I can generalize my Anderson model to what's called the Coquelin-Schrieffer model. And so here I have changed my label from sigma to alpha, and alpha, yes. Okay, so we'll get to a Kondo model in a minute, but alpha ranges from 1 to n. And so I'm doing this for both my conduction electrons and for my F electrons, which are still real F electrons. And so alpha, there's 6 alphas here. And now my empty state is still just a singlet, but my doubly occupied state becomes much more complicated because I have both inter and intra-orbital Hubbard U's, I have Kuhn's coupling, lots of terms that I'm not going to write down. But you get a bunch of states here, and it's generically, you take this, just the fluctuations to the lowest one, which you think is the singlet. And then there's also 4F3 through 4F14, which we're going to assume are much higher energies, and we're going to neglect that. Okay, and often what we'll do is we'll just actually throw out this entirely, say, well, this is the lower energy scale, so I'm going to set U to infinity and only take this degree of freedom, that's the infinite U Anderson model. But at any rate, you take this with this Coquelin-Schrieffer model, where here I'm assuming everything is nice and SUN symmetric, and I integrate out my higher energy degrees of freedom, and I also get a SUN Kondo model, and I should have put more labels here, but this is a Kondo coupling between the, these are gammas, or these SUN operators, so I'm generalizing the SF, which had 3, SZ, SX, and SY, to gamma, which you can, for SUN, label them with alpha and beta, where alpha and beta range from 1 to n. So for SU6, or SU4, say, there are 15 different of these generators. And you can make them also out of these conduction electron ones. Anyway, this is just the way you typically will write this down. You can also write it down just like a dot product between SUN operators for conduction electrons and spins. Okay, so, but real life doesn't look like this either, right? Because in real life, we don't have this full degeneracy because we're not sitting in free space. So we have what are called crystalline electric fields, and these break the SUN degeneracy in different ways. So here, I'm going to give you an example in hexagonal symmetry because this is sort of a particularly simple case to explain it. So in hexagonal symmetry, you break your j equals 5/2 into 3 different doublets. And you can label them. Typical labeling is in terms of these gammas, but these are the JZ quantum numbers. So they're plus or minus 3/2, plus or minus 1/2, and plus or minus 5/2. And so now, instead of having the same hybridization for each of these crystal field doublets, we have a different one. So we have our V is labeled by gamma now, where gamma is 7, 8, and 9 in this case, and alpha is the plus or minus parts here. So these are now SU2, describing each of these 3 different doublets. So we've broken the SU6 down to SU2. All right, so now we really need to address the question, because here I've written this as this psi alphas, which is a little different from these C sigmas. And so we have to ask, what is actually hybridizing with our F electrons, right? So we know that it has to be a state that has the exact same symmetry as the F electrons, but it's not coming from F electrons on the same site. It's going to be coming from, say, I don't know, it could be cerium D electrons on other sites. If you're in a compound with other materials, it could be coming from other ligand atoms. These are your C's, and so here I'm just taking them to have a single label sigma, which is plus or minus 1/2. And you can construct Wannier states with the same symmetries as the F electrons that sit on your local states that have, by using some kind of form factor here. So this is a matrix between sigma and gamma alpha. It is K-dependent, and it has interesting structure. And so this can give you hybridization that has structure and momentum space. But when you use these Wannier states, you can then go ahead and do the Schrieffer-Wolff again, and you get an SU2 Kondo physics for your, say, lowest energy doublet. And so this is how you sort of get your different Kondo channels. So here, I'm going to first throw away the F2 states. So I'm only looking at these valence fluctuations from F1 to F0 from my ground state plus or minus 3/2 doublet. And this is what the electron cloud looks like for this case. And so the first Kondo channel is going to have this symmetry. So you're adding and removing electrons with this symmetry from it. So your Wannier states have that symmetry. And you can, when you do your Schrieffer-Wolff, your Kondo coupling for this channel will be like the V for this channel divided by the energy cost for this channel. And then you can also have a second channel. So here, say we excite from, we add an electron to our ground state, which has this gamma 9 symmetry. We can add an electron that's gamma 9, which would be boring. That would give us the same channel again. We can add a gamma 7, or we can add a gamma 8. And so if we say add a gamma 7, then, and this is a singlet, then we say we have a different Kondo channel, which has the symmetry of this Wannier state that we're adding, so it's gamma 7. So this is what this one looks like. And this will have a different Kondo coupling. It's like this V7 over whatever this energy is that I don't want to write out. And then I can have a third Kondo coupling if I'm adding a gamma 8, this plus or minus 5/2, and that gives me a different excited state. Again, this is what this looks like, and this will have a different third Kondo coupling that has a different symmetry here. So, yes?
Do we have something like an interference between gamma 7 or gamma 9, like a 9 times 7?
Yeah, so, okay, so life is a little more complicated than what I'm showing you here, and so maybe hold your question for when a similar looking slide comes back in like 3 or 4 slides. Because life is a little more complicated, but I want to just give the idea of like how you can get channels here. So this is how you get different channels, and the key point here is this is all you can get, right? If there's many more states up here, but they're all going to have basically these 3 channels because those are the only ways you can add add electrons to these. These are the only conduction electrons that are available to add here. Okay, so even if they're coming from fluctuations to here and fluctuations to here, they give you the same channel if they have the same symmetry. That's the key point here. If they have different symmetries, they give you different channels. And normally, we ignore both of these other things because this one is much stronger, and the second Kondo channel we'll see is irrelevant if they're not equal to one another. All right. So now I want to talk about where we really tend to get 2-channel Kondo physics from. We've sort of introduced this basic idea. And so, as I said already, we have strong spin-orbit coupling. This ties together your J's, your L and your S's into a J. Your J can now either be half integer, as in the cerium case, or it can be integer, which will be if you have, say, praseodymium, which is 2 F electrons. And we know that moments have different behavior under time reversal symmetry, depending on whether they're integer or half integer. So integer J states behave sort of like we normally expect. They behave like a vector under time reversal, which I'm representing with theta here. they pick up a minus sign. Under double time reversal, they return to themselves. Whereas if I have half integer spin states, they are represented by spinners. If I do a single operation of time reversal, I get to an orthogonal state that I'm representing by theta times psi. If I do a second operation of time reversal, I pick up a minus sign, and it's only after I do 4 that I get back to my original state. I really like this picture. This is a Mobius strip. So if you do like a pi rotation around a Mobius strip and it's sort of uniformly twisted, you get something orthogonal. If you imagine the vector pointing out from this edge here, and it's only when you've gone around by 2 pi, you're pointing now in the opposite direction. You go around all by 4 pi, you get back to yourself. So we expect different physics here, and this will be important later also, but for now, the main consequence that we're interested in is Cramer's theorem. So this tells us that half integer J multiplets, because under time reversal, they give you an orthogonal state, those have to be at least doubly degenerate. So Cramer's doublets are protected by time reversal. So as long as you have time reversal in your system and you have a half integer J, you will have at minimum doublets. So that's why serium, you can always draw those 3 doublets. So no matter how low your symmetry is. But integer J ions don't have that protection. So you can have, in the lowest symmetries, you'll just have some number of singlets. But if your symmetry is high enough, you get lucky, you get what's called a non-Cramer's doublet. So this is protected by the crystal symmetry. So here's sort of a generic picture. This is what happens in tetragonal symmetry. So for odd J cerium, you get your 3 doublets. For even J, praseodymium, which has J equals 4, you get 5 singlets, but there's actually 2 doublets in there. And for cubic symmetry, you get also a doublet and some triplets. Okay, and these can be magnetic or non-magnetic. So I'm going to talk about 2 examples of these non-Cramer's doublets. So the simplest one is in cubic symmetry. So this is J equals 4. So you can write the 2 states of your doublet. It's called the gamma 3 doublet. They're unrelated by time reversal symmetry, obviously. So this is 2 plus minus 2. This is 4 plus minus 4 minus 0. You can calculate the charge density associated with them. This is in cubic symmetry. So essentially, this plus state of this doublet is squashed, and the minus state is elongated. And those are degenerate under cubic symmetry. But clearly, if you break cubic symmetry, they will break the symmetry. And this is what's called a quadrupolar doublet. There's no dipolar expectation values here. The non-zero expectation values you can get here are the 3jz squared minus j, the jx squared minus jy squared, and then you can also get jx, jy, jz, which is an octopolar expectation value. So if you have this and it's ordering, you can get quadrupolar order of these 2 types, or you can get octopolar order of this type. Okay, good. So this is one of the doublets, and this one I really like because it's just got a label that is its shape. It's quadrupolar degree of freedom. Now, if you're in lower symmetries than cubic symmetry, you don't get such nice quadrupolar doublets. You generally get Ising magnetic doublets. So in tetragonal symmetry, again with J equals 4, you can get this mix of Jz is plus or minus 3 halves and Jz is minus or plus 1 half. So this has no dipole moment in the plane, but does have a dipole moment along the z-axis. And then in the plane, it actually has these quadrupolar expectation values. So it's a mix of quadrupolar and dipolar degrees of freedom. Okay, but both of these, you lower your symmetry, you lose the doublet. Okay, so, and this is, you can also get these in trigonal and hexagonal symmetries, and that's it. If you go down to orthorhombic, there's no possibility of this, these doublets. Okay, so now let's talk about what happens to Kondo physics when I have these non-Cramer's doublets. So in cubic symmetry, you have this quadrupolar doublet with these 2 shapes that are representing the 2 levels. And when I have valence fluctuations, I'm just going to take one way. So I'm going to go from 4f2 to 4f1. And my excited state then is a 4f1 state. That has to be a doublet. It's guaranteed by Cramer's theorem. So this is what, I'm picking a particular one. This is what its shape looks like. and then there's two spin degrees of freedom, essentially. This is this plus or minus. Okay, and so then I have valence fluctuations between these two states. And these are conduction electrons that are sitting in Lisbonne states on this local, on this F site. So they'll also have some shape, and you notice one of them is squashed and one of them is elongated. So they also have a quadrupolar moment degree of freedom, essentially. They have a shape that matches with these guys. But they also have spin 1/2 degrees of freedom. And so they get there are 4 of these. That's why I've written 4 arrows here. They're going in. Anyway, right. So there's 4 states here to take us between these 2 states to these 2 states. And so this is basically 2 different Kondo channels. But because our SU2 doublet is represented in this shape space, essentially, the channel here is spin. So this plus or minus that we had before is now our spin, is our channel label. Okay, and so when we do a Schrieffer-Wolff on this particular simple case, we get a Kondo coupling that is now between, I'm using tau to represent the quadrupolar moment. So I have F electron quadrupolar moments, tau F, and then I have conduction electron quadrupolar moments, which are in this sort of, alpha is representing the doublet down here, so this is labeled by alpha. Sigma is representing essentially this excited doublet, and the conduction electrons have both labels. So this is this can be off diagonal in alpha and beta, which is our pseudospin index, but it is diagonal in sigma. But the Kondo coupling is the same because I have time reversal symmetry. So this Kondo, the degeneracy of the 2 Kondo channels is guaranteed by time reversal. So, okay. So now, so now I want to go back to this just to give you a flavor of how life is actually a little bit more interesting. So really when we have the cerium and hexagonal symmetry, if we're looking at these excited states, the excited state is actually not a singlet. It's actually, if I pick this guy to be my ground state, the excited state is guaranteed to be a doublet. So this, if you don't know a lot of group theory, this is not so helpful, but you can look it up in point group tables. These guys are both doublets. So this is saying if I add, if I take my doublet ground state, I add the conduction electrons that are available, either way, I get a doublet. And so this means that if I just look at this Kondo channel, these 2 energies are the same. And actually, I'm guaranteed to get an intrinsically 2-channel Kondo model when I do Schrieffer-Wolff for this, this way of fluctuating to the doubly occupied states. But I don't get just I'm not going to write it down because it's ugly. But just to give you a flavor, you get not a simple, so you're guaranteed to have 2 channels, but it doesn't look like a normal Kondo model that I've been writing down because it's actually asymmetric in the spin degrees of freedom. So you get a Kondo coupling for your Z component that looks like V7 squared plus V8 squared. And you get a Kondo coupling for your perpendicular components that looks like V7 times V8. And then you also get another term that I don't actually know exactly what it looks like for this one because I didn't do this particular derivation. But it will be something that's not even just a pure spin Kondo term. There's some channel degrees of freedom mixed in. Okay. We generally ignore all of that anisotropy when thinking about this physics because we know from solving impurity mode the spin anisotropy between these like JKZs and JK perps is irrelevant. We also generally ignore this entirely because this one is way stronger in cerium, and so we just focus on that for cerium. But I just wanted to give you a flavor. If somehow these guys were tuned, you would get 3 degenerate Kondo channels. Okay, so I'm going to wrap up here. We're going to continue tomorrow, but let me just give you sort of the basic flavor of the weirdness in this case, and then we'll get to the more mathematical results next time. Okay, so this is what we showed you before, right? We have our 2-channel Kondo physics. So now now if I start off, I have a net quadrupole moment. So I'm representing this with an arrow, but it's in this quadrupole moment state. And I have conduction electrons that have this quadrupole moment. So they come, and they both try to screen it. So they have their quadrupole moments, which are these arrows, and then they have their actual spin degrees of freedom, which are plus or minus. So here, they've done too good a job, right? You get a net quadrupole moment of -1. And then I go and bring in 2 more conduction electrons that try to screen that net quadrupole moment. And now I get back to +1. So this is now 2-channel, so this is now overscreened, right? So what you get generally from overscreening is instead of having the strong coupling fixed point that you get from single channel Kondo physics, you get an intermediate coupling stable fixed point that is intrinsically quantum critical. And so you can write down, so I'll just flash this. I think this is a good point to end for today. You get if you tune the couplings of your 2 different Kondo channels, so they're related by time reversal symmetry at this point, but you can tune them. And so if you have one is larger than the other, say your up spin Kondo is larger, you will just quench the quadrupole moment by only your up spins and up conduction electrons, and the other conduction electrons will decouple. Or you'll quench it by only the down spin conduction electrons, and your up spin conduction electrons will be decoupled. But in between, you get this quantum critical point. And this is really interesting, and we'll talk about this next time. But one of the key features is you have a 0-point entropy associated with your impurity, and this hosts a single Majorana fermion. So we'll talk about that more next time. Does anyone have any questions now? Yeah.
I had some questions about the free-for-all the hierarchy of scales. So as I understand it, I do my free-for-all transformation, I'll replace a linear coupling with quadratic coupling via some gauge. Is that what you're doing here?
Let's see. So let's go back to just the understanding. So. Okay. All right. So what you're essentially, you are essentially replacing this sort of bilinear coupling with quadratic coupling here. So you can represent this recognize this S as like an F dagger sigma prime F sigma essentially. So there's actually a bunch of other terms that we generally throw away because they're not so interesting. But that's the basic idea, yes.
Yeah, so B is your lowest energy scale. You assume that it's lower than the F.
Yes, so you're essentially integrating out these energy scales. I mean, you're doing a canonical transformation that, yeah, you expect that this JK is small. And so if it's not small enough, then you should, in principle, have higher order terms. In practice, Kondo physics tends to, Kondo and Anderson physics tends to sort of describe a continuum. And so you might not be exactly in the Kondo limit, but you'll still have the same basic physics. One thing you'll note, this is the Anderson model, but if you remember the mean field that I wrote down earlier, where they were not real F electrons, it looked basically like this exactly, except it didn't have a U-term because we were sort of enforcing the half building exactly. So you get the same physics more or less from Anderson to Kondo. It's just you're sort of going from having real valence fluctuations, you have real occupations of these states, to being fully half integer or merely integer filling for this Kondo state.
So I was wondering about the properties of this Kondo Phy.
Mm-hmm.
Is that something one can measure? Get some properties like the Venn scale?
That's a good question. I know that people have looked into that, and but I'm not really, so it's like there is a Kondo length scale, which should be like h bar over tk, and I don't remember right now. People have done this in like STM, for example. Yeah, I do know that like if you start to worry about like, oh, let's say I have a really dilute system where my clouds are really small, you might worry that like, or sorry, no, sorry, I don't want to, never mind, I'm not going to say that. So yeah, so I don't know, it's a good question. Yes?
Thank you for the great lecture. So I have two questions. The first question is that in your Anderson model, your V, your polarization V is a constant, it's not dynamic.
Yes, so this is a bare hybridization. Yeah.
And my second question is, when what is the picture like when you have interaction with that?
Yeah. I mean, that can make life significantly more complicated. I think, you know, heavy fermion physics is still one of the things that can happen. I don't think that interactions in your bath will necessarily modify that basic state itself, but they can then cause other things to happen. Yeah.
We have time for one last question.
I think he was first, actually.
Could you elaborate a bit on the last line, why the intrinsic is intrinsically quantum critical?
Sure. Yeah, so this is basically just because, okay, so I'm going to elaborate a lot more tomorrow, so I'll mostly leave it for that. But when you have this two-channel Kondo, with this non-Kramers doublet, these two channels that I'm labeling here with JK sigma are actually guaranteed to be generate by time reversal. So you're guaranteed to sit at this point where it's not sure if it wants to form a heavy Fermi liquid with the upspins or with the downspins. And so what I'll talk about next time is what the properties of this quantum critical point are. Show you that it is a quantum critical point, but it's intrinsically degenerate because it's protected by symmetry of your system. So it's not reached by fine tuning.
All right, let's thank Rebecca again for her great talk.
Thanks.